Okay, so now we're going to continue with making how we can make alcohols different ways. So we've gone over, so far, we've gone over the ways we can make alcohols from the SN2 or the SN1 reaction. We've gone over reactions of alkenes, and then we went over like the reduction of a carbonyl compound, which is the new reaction that we've gone over via hydride. And now we're going to continue that reduction, but we're going to go from hydride to a new reagent, and we're going to be introduced to what we call the Grignard reagent. So the Grignard reagent is a molecule where you take an alkyl halide and you react that alkyl halide with a metal, in this case magnesium, and that magnesium inserts between the carbon and the halogen to give you this molecule here that we call a Grignard reagent. This reaction can happen for whether that center, whether the carbon halogen bond is for where the carbon's sp2 hybridized or sp3 hybridized. It's a pretty broad. It's the spectrum of what you can make Grignard reagents with is really, really broad. So we can use the bromide, the chloride, it can be sp2 or sp3 carbon, whatever. And then you make this reagent here. The reason the Grignard reagent is interesting is because when you look at the Grignard reagent and when you look at the electronegativities of the atoms in that between the carbon and the metal, metals are pretty, the electronegativity of metals versus nonmetals is usually lower, which is we see up here. So the electronegativity of carbon is 2.5, the electronegativity of magnesium is 1.3. That difference is significant enough to make it so that when you make the Grignard reagent, we actually don't want to think of the Grignard reagent as this. We want to think of the Grignard reagent as this, as a carb anion. And as we know, when we start putting a negative charge onto an atom, that makes that atom a strong nucleophile or a strong base. So in this case, these Grignard reagents are carb anions where the carbon is nucleophilic and basic. Super important, right? One of the things that we have to consider is that if we want to make more complicated molecules, we have to be able to make carbon-carbon bonds. We've gone over a number of different ways to make carbon-carbon bonds, right? Like the Diels-Alder reaction or using the acetylide anion. But this is now a new way we're going to be able to make carbon-carbon bonds using the carb anion because now this is nucleophilic. And the reason why this is useful is because if we can make R minus, well, that R minus can attack a carbonyl compound because this carbon here is partially positive, right? So we know that this carbon right here is partially positive, making this partially negative. This is more nucleophilic, that's electrophilic. Nucleophile attacks the electrophile, pushing the electrons up. So there's a nucleophilic attack step here, followed by a protonation. So this is always a two-step process. This is always a two-step process. And the reactivity of a Grignard reagent is very similar to the reactivity of lithium aluminum hydride if you had to compare the reactivity of the Grignard reagent to the hydride. So Grignard reagent will react with aldehydes, ketones, and esters, but it will not react with the carboxylic acid. And again, it's a two-step process. The first step makes the alkoxide, and then you protonate the alkoxide in a proton transfer, so boom, boom, to give you the final alcohol product. Now, one of the things is you have to be careful when you use Grignard reagents because Grignard reagents are also strong bases. So if we see this acid-base reaction, the pKa of water is 15.7. The pKa of a sp2 or sp3 hybridized carbon is somewhere on the order of 50. So if there's any acidic protons, and the protons don't even have to be very acidic, alcohols, water, even sometimes amines, those will all those will all react with the Grignard reagent before the Grignard reagent can react with the carbonyl. That's why when you do these Grignard reactions, you have to do them in the absence of water. It's called anhydrous, and you usually use ethers as the solvent, something without a protic, a polar aprotic solvent. So you can't have water around, and you need a polar aprotic solvent. So let's come up with so why don't you take a second, pause the video here, and try to come up with the products of these reactions here. All right, welcome back. So hopefully you took some time to try to come up with the products of these reactions. When you see the Grignard reagent, what you immediately want to be thinking about in all of these cases is you don't even want to worry about the actual, you want to write out what the carb anion is. So the carb anion here is going to be the CH3 minus, okay? Now, once you see the Grignard reagent, this is going to be an addition reaction. This is a nucleophilic addition. That's what this type of reaction is called. So these reactions between the Grignard reagent and a carbonyl, these are called nucleophilic addition reactions. All right. So what's going to happen here is we're looking. This is your nucleophile. That's your This is your electrophile. So here to here, and I'm going to go ahead and then There's the protonate. So I'll go ahead and draw up here kind of what that intermediate looks like. So you have the O minus. You have your methyl group that you added. That's the end of the first step. The second step is the water to protonate the alcohol here. Push the electrons up here to give you the alcohol as the final product, where you've made a new carbon-carbon bond here. So here again, this is going to be your Grignard reagent. This is the carbanion. Once you make the carbanion, if you recognize that this is a nucleophilic addition, so what that means is you're going to attach the nucleophilic carbon to whatever the electrophilic atom is. That's here. That's going to add here, and then you're going to get rid of this bond and make the alcohol. So that's how you can come up with the product without having to draw the mechanism. So I'm going to make the alcohol, the carbonyl becomes the alcohol, and then I'm making a new bond to my Grignard reagent. Now the only difference here is that analogous to the LAH, the Grignard reagent adds twice to give you the product where you've added 2 methyl groups to this carbonyl carbon here. Okay, so these reactions are directly analogous to LAH. We're just replacing the H minus you're adding with whatever the Grignard reagent is. So all of these reactions use methyl magnesium bromide, but you can use a number of different. You can make the Grignard reagent from a whole slew of things. All right. Okay, so I hope that made sense. Let me know if you have any questions. And one thing to keep in mind, like I said, is that the Grignard reagent will not react with carboxylic acids. And the reason is if I have a carboxylic acid, just like we showed in the previous slide, and regardless of how much of the Grignard reagent you use, it could be an excess of the Grignard reagent, right? I could have an excess of this Grignard reagent. But what's going to happen here is that this R minus is going to remove this proton, and you make the carboxylate, the O minus here, plus the protonated Grignard reagent. Now, in the LAH case, LAH is reactive enough to keep reacting with this very unreactive carbonyl carbon. Once you make the carboxylate, from a resonance standpoint, this oxygen is pushing electrons toward this carbon, making it less electrophilic. But LAH is reactive enough to overcome that. The Grignard reagent is not, so the reaction stops here. So you don't, when you take a carboxylic acid and react it with the Grignard reagent, you deprotonate to make the carboxylate, but you do not add to the carbonyl carbon. All right, so that's making alcohols from Grignard reagents. Let me know if you have any questions. Thanks, and have a great day.